Linear regression is a simple and useful technique for prediction that will also help us illustrate many important principles of machine learning. Recall our supervised learning paradigm. We have some observed features x, which we would like to use to predict a target value y. We create a flexible function called a learner, whose input-output relationship can be adjusted through some parameters theta. Then a collection of training examples are used to fit the parameters until the learner is able to make good predictions on those examples. In linear regression, our learner consists of an explicit functional form. In other words, we define a family of functions parameterized by theta, and any particular value of theta defines a member of that family. So for example, we would compute theta 0 plus theta 1 x1 to produce an explicit relationship, linear relationship between the feature x and our target y. Then learning finds a good member within that family, meaning a good value for the thetas, using the training data set D so that our predictions match those points. Some quick notation: our prediction y hat is a linear function, theta 0 plus theta 1 times feature 1 plus theta 2 times feature 2, and so on. And for notational compactness, we'll define a feature 0, x0 for every data point, that always takes on value 1. Then y hat is simply the vector product between a parameter vector theta, consisting of theta 0 through theta n, and a feature vector x, consisting of this new feature 0, the constant 1, concatenated with our n features. We also need to define what it means to predict well. Define the error residual to be the signed error between the true or desired target y and our predicted value y hat. If our prediction is good, these values, shown here as little blue bars from our prediction, the black line, to the true value y, will be small on average. We can measure their average squared magnitude, for example, the mean squared error. So 1 over m times the sum of the differences between the true values and our predictions. We'll define our cost function, j of theta, that measures how good of a fit any particular setting of theta is by summing up the squared error residuals over the training data. While we could easily choose a different cost function j, and we'll discuss some at another lecture, mean squared error is a common choice since it's computationally convenient, and it corresponds to a Gaussian model on the noise that we're unable to predict. If this noise is the sum of many small influences, then the central limit theorem suggests that such a Gaussian model might be a good choice. Since we're using MATLAB and its vector and matrix operations, let's rewrite this function j in a more convenient vector and matrix form, where we use the parameter vector theta and a vector of our targets, a column vector of the target values, and a data matrix x, where each row corresponds to a data example, so example 1 through example n, and each column corresponds to a different feature, so the constant feature and then feature 1 through n. Then our cost function is just the inner product of the error residuals. So the error residual vector is y minus our prediction vector, theta times x transpose, and taking the dot product we get the sum over all the data points. In MATLAB this is very convenient. We can just compute the error residual e as the difference between the vector y and the vector theta times x transpose, and then we compute its total average magnitude by, say, e times e transpose divided by m. So, now that we've chosen a form for the learner and a cost function, learning for linear regression just comes down to selecting a value for theta that scores well. The cost function j of theta is a function of the parameter values theta, so we can plot it in a parameter space. Suppose we have a linear function, theta 0 plus theta 1 x, so we have two parameters, so we plot 2 dimensions for that and 1 dimension for j, so it's a 3D plot. The 3D is a little difficult to look at, so we can plot the value of j as a color, with blue being small values and red large, and we get the following color map. Even this is often inconvenient to draw, so we'll often just visualize the contours or isosurfaces of j. So for any value of j, there's a surface that's formed by the values of j of theta that take on that particular setting. And if we just find that set of points, we can plot that with a red line. And then plot those contours on a space where just theta 0, and theta 1 are expressed, showing a sort of topological map of the function j, where here the minimum is in this place and increases happen with the contour lines. Given a representation of the cost function j of theta, the problem of learning is converted into a basic optimization problem. How can we find the values of theta that minimize j of theta? In the next segments, we'll explore several methods of doing so.